So we are looking today at cylindrical shells, volumes of solids of revolution. Now for this class right here, you guys have just written the AP exam. You did a little work on your project now. This is the rest of the course for the 30-hour locally developed course. We're doing methods of integration for the most part for the rest of the semester. So it is a semester class, so yeah, we aren't done after the AP exam. We have to keep going. We have another month or so to go. And this is the first up, the cylindrical shell method of volumes of solids of revolution. Now you didn't need this on the AP exam. You tell me after this, I guess, whether you needed this on this year's AP exam. But solids of revolution were on there. There's, yeah, you don't know. I don't know. Maybe we needed it. I didn't see a question where we needed it, but okay. So anyways, you could have done solids of revolution using the washer or disk method. And we're going to just review the washer method real quick here. And I'm going to show you how in certain cases with certain revolutions, the cylindrical shell method is superior, much easier. And so that's the first thing we're going to learn here post AP exam. So recall washer method. All right. So if we were rotating here about the y-axis, okay, we want a volume of solid of revolution that goes from, let's say, 1 to 4 and caps out here at, we'll make a y value here. Okay. So it's this, basically it's this thing right here, and we want to revolve this around the y-axis, okay? So each kind of corner is getting revolved. So we have, you know, something like this, right, roughly, and it's rotated through space, okay? So the washer method is great if, and here's the big if, right? If we have the same function as the sort of outer function, right? The outer function, and the same function as the inner function throughout the interval. So think about this. If we're taking a look at this area, we are going to find the three-dimensional, you know, the solid made by the outer line. That's the big kind of bowl there, right? Solid through bowl, and then we're going to subtract this. Right? So I won't go over this again too much, but you can see that this is a pretty straightforward way of doing this, the washer method. Now I'm going to give you a couple examples where this washer method is going to get tricky. Okay, and this is going to sort of make you aware of the need for this cylindrical shell method. So let's just say, now you can copy this down or you don't have to copy this down. I would suggest that because this is the first example where we have a description of the shell method, you might want to copy this down. So if we were to find the solid bounded by y equals x plus 1, which would be this line, x plus 1, let's say, x equals 1, and x equals 3, okay, and obviously the x-axis as well. I didn't write that, but it's the x-axis as well. So we've got kind of this shape going on here, okay. And we wanted to rotate this solid around the x-axis. Okay, so it's basically, this is kind of the other side of it, right? We're rotating this around. Now, the washer method. So in this washer method, what you would have to consider is you'd have to consider that we would have a washer or stacks of washers. Sorry. We would have stacks of washers that would kind of look like this, right? They would stack up here, and we would take this middle part away. But it would only be good, we would only be able to stack washers till this point right here, till this horizontal point right here, okay? So I'm going to erase the washers there now. I might just zoom in so you can kind of see this. Okay, full shot here. But we would have to stop there because we now have a different set of boundaries. So let me just erase some of this. So at this point, we'd have to stop because right now we have x equals 3, right? And we have x equals 1 as our two functions. But above this point right here, now we have two different functions. We have x equals 3, and then we have y equals x plus 1. You see that? So we're going to have to do this twice. We're going to have to find this rotational section right here, and then we're going to have to find, you know, this rotational section here, okay, roughly like this. So we're going to have to split that up because the outside function and the inside function is not consistent throughout the entire solid. All right. Now the shell method. Okay, the shell method simplifies this because what we're considering is we are building our solid of revolution not of discs or washers. So discs would be a solid, a solid flat circular plate. A washer would be a hollow flat circular plate, right? That's a washer where we have a bored out center, let's say. So this is disc washer. The shell is this. What we are considering is we are considering the outward wraparound part of a cylinder. So here's a cylinder that we're considering. That would be the bored out sort of middle part. And what we're looking for is we're looking for the area of this wraparound part of the cylinder. And instead of stacking washers one on top of the other like this, what we're considering doing is taking a cylinder, okay, so a cylinder, and then we're getting slightly larger cylinders and putting that, sliding that over top, slightly larger cylinders yet, sliding that over top, over top, over top, okay? And so that we are building this solid through the wraparound parts of cylindrical shells. So we're taking the shell part, the outside part, and we're taking that area and stacking those around this way. So instead of washers stacked up like this, it's shells, little shell, outer shell, bigger shell, bigger shell. And we're going all the way to here, and we're considering the wraparound shell parts here. And that's going to build our three-dimensional sort of sweep through space there. It's going to be the outer wraparound parts of these cylinders. So you remember from grade whatever, probably nightmares here, but remember drawing a net diagram for a cylinder? Right?
Yeah, grade 9.
Yeah, grade 9. Okay. So the wraparound part here is just a rectangle. Okay, so this is nice. That's nice. If we just took that rectangle and we wrapped it around, there would be a radius. This would be a circumference, obviously. This is a circumference. And this would be just the height. Now, the nice thing about this situation is it doesn't matter, what sort of functions we have sort of in the left to right here. All we need is we need a height. We need to be able to find the height. And here there's only two functions involved for this height. So this is going to be really easy. Okay. Now, I'm going to keep showing you examples through this, but that's the first part of the cylindrical shell. Now, here is a diagram. I wouldn't copy this down, just watch. This is y equals 1 minus root x, okay, this function right here. And this is the vertical line, -1/4. If we were to wrap this around, okay, if we were to wrap this around, then we would have, washers built up, right? And we would end up with this solid. This would be the solid of revolution, okay? And the one way to do that would be, like I mentioned, the washer method, right? We have, a large washer, and then we would stack these washers around and so on, and they would be hollow, so we're subtracting this middle part always and so on, right? That's the washer method. The cylindrical shell method looks like this. Here's my first cylindrical shell that I deal with. It's this part right here, and I'm considering the wraparound part. The next one would slide just over top of that. I'm going to dramatize this. I'm going to exaggerate this, but here's the next one. It's a little bit bigger, but it's also a little bit shorter because the graph kind of goes down here. And so we have this outer part of the cylindrical shell. Then the next one, I'll put in dark blue, the next one slides over top of that yet. And so what's happening is the radius for this cylinder is growing, but the height is decreasing. And there's just sleeves, right? One over top of the other, okay? Sleeves. And the sleeve part is what we are going to add up. So again, we're going to be adding up an infinite number of sleeves. Yeah, you like that? Kind of like a mime. You like that?
That's what I was trying to do it, but I can't do it quite.
Okay, yeah. Thank you. So if we slide those sleeves over top, we're going to anticipate an infinite number of those, right? So we're going to be sliding an infinite number of them. As we get to the end, notice that the height gets really small here and the radius gets really large. Okay? And so these get really, really short and really wide until it gets almost to like 0 here at the end, right? So we're approaching sort of a height of, 0 as this reaches the axis. See the height of 0 right here. So the heights they get smaller and smaller and smaller. And the height is just, what's nice about this, the height is just the value of the function. Okay? So what is the circumference of a circle? What's the formula? Pi r squared is the area of a circle. Pi d, or 2 pi r. We're going to do this in terms of r. So circumference is 2 pi r. All right? And the area, as we mentioned, we draw the net diagram here. The area of this wraparound part is 2 pi r times h. So the 2 pi r times h. The h just happens to be the function height in this simple example. So we've got 2 pi times h, or times y, the function height. And of course, we're going to let this go from, from this starting point out to this starting point for r. Okay. Now, we do have a axis of rotation, so there's a midpoint in here. So this is going to change slightly. We'll talk about that in a second. But I want to show you how the cylindrical method can really simplify a very difficult washer method just one more time, and then we're going to actually do one here, okay? And you'll see how this is going to make certain problems much easier. So I'm going to navigate away from this, and I'm going to go to this one right here. You can copy this question down, but I wouldn't start working on it yet because, again, I'm going to contrast for you one more time how the washer method could be done and how it's actually pretty tricky to do the washer method, but easy to do cylindrical shell. So this question, we're going to end up doing this with the cylindrical shell method. So again, you can copy this down. But the washer method, I'm just going to kind of set this up in a diagram for how this would be solved during the washer method. Then we'll do it with the cylindrical shell method. So find the volume of the solid formed by revolving the region bounded by these graphs. So y equals x plus 2, that's the red graph right here at the top, the upper boundary. Y equals x, that's the blue graph, that's this lower boundary here. And x equals 3, and the y-axis. So we've got the y-axis here, and we've got x equals 3. So basically, here we go. This is our region right here that's bounded. And what we're trying to do is we're trying to revolve that around the y-axis there, okay? So it's spinning all through space, this sort of angled, right? Like this, right? Can you see that? Now, x equals 3 right here. That's right. This is x equals 3, this vertical line, and here's x equals 0. All right. So this looks fairly straightforward. Like here's the other half of it, roughly, right? Here's the other half of it, and we're just revolving this around in space. But the washer method, we have to consider this, that we actually have discs, solid discs with no hollowed out middle, from about 0 to about 2 there. So these are solid discs that we could stack on each other, no problem. We now have to switch our thinking because there are now, from the y-axis, there are 2 different functions. I have to consider this function, y equals x, and this function right here, y equals x plus 2, but I have to cap this right here. See, now I take the blue graph, and I have to flip this around in space. You see? So there's part number 2. Part number 3 is going to be in yellow, which might be a little difficult to see with all the lights on, but here's part number 3. You see that? Because I have different functions yet. I have x equals 3 on this side as the far function, and I have y equals x plus 2 as the near function. So we have to rotate, we have to do washers for 3 different sections. You can turn the lights off if you want, if that's easier for you. So we have to do washers for 3 different sections, if that makes sense. So the washer method is going to be 3 different integrals that we have to add up all together. Okay, and again, each of these are linked by, rotating around, right? So these are rotated and everything. So the washer method, tricky, not impossible, but tricky. 3 different integrals. The cylindrical shell method. Okay, so we will do this one now from scratch. And the cylindrical shell method, notice that we are rotating this thing around a vertical axis, but all we need is for the cylindrical shell to be really easy, is we need the same function to be on top and the other function to be on top the whole time as we move in the x direction. So the height of the cylindrical shell is going to be the height difference, or the difference between function 1 and function 2. So for cylindrical shells, this is the height. You see that? For each one. And I'm going to go all the way to this green line. Okay, that's y equals 3, height. So here's the height always. The radius, because we're going to try, we need 2 pi r h, so 2 pi constant. R is going to be, the radius is going to grow as x grows. So we're going to go, the radius is going to be simply x going from 0 to 3. Now initially it's going to have a radius of 0, because really we're looking for the very first cylinder if we were counting them. Of course we can't count them because there's an infinite number, right? So we can't count them. But the first cylinder would sort of look like just this solid line here. It would have a radius of 0. Okay, so we can't really see it. But the first little sliver of a cylinder would be really, really small, right? The radius would be super small, and you'd have, here's your first cylinder, like this. And it would be this wraparound part right around the y-axis there. Okay. The next one, if we link up with this line right here, the next one would have a radius like this. And so again, we are kind of drawing these cylinder shells, and I'm just going to draw a few of them. This one's going to go all the way out to here, let's say. Okay. And I apologize for my really messy cylinders, but there's another one. So it's bigger, it's wider, and the height actually ends up to be a constant here, doesn't it? If you notice that this height is actually the same all throughout. It's not going to be for every one, but we just want to stack these cylinders on top of each other as it kind of grows upward like this. We're getting bigger cylinders, and that's going to be that's going to form, once we stack all of them, nest all of them into each other, that's going to form our 3-dimensional solid. So how do we go about this? Let me erase a couple of these things here. How do we go about this? Well, we want to find out the circumference roughly equals 2 pi r, right? And the area of each cylindrical shell is 2 pi r h. So the area is 2 pi r h. Those are the areas that we are concerned about. So we want to stack an infinite number of these wraparound parts. So we are talking about an integral. To find the volume here now, we are going to take the integral of 2 pi. Now r, we have to figure out what r is, and we have to figure out what h is. Okay, 2 pi r h. And the little differential in x would be the width, like the minuscule little width of each of these wraparound parts. And that's where the dx comes from. It's just the sort of the thickness of the wall.
Please call 205. Mr. Glasgow, please
Okay.
call 205.
So what is r? Well, the radius of the circle here that would rotate through space, you can see, starts at 0 and goes to x. So this is just x. And x is going to grow, right? You see, x is going to get bigger and bigger. So this is just x. The radius is just x. Really nice and straightforward there. The height, now the height here, h, we said, throughout this whole, from 0 to 3, is going to be the difference from the top function minus the bottom function. So this is going to be x plus 2 minus x. And we want to stack these cylinders, okay, as the radius grows in the x direction from, the center is going to be from 0. So we're going to start at 0, and we're going to go to a vertical line of 3. So we're going to have 0 to 3 right here. So again, these wraparound parts would represent in space, this wraparound around the vertical y-axis there. So the axis of rotation of this whole solid. So if you look at that thing, it's this sort of angled piece. We're gonna bring that around, and then keep rotating it around through space, right? So we're gonna find out what that solid is. It's rotating around a vertical axis here. Yes.
Does this method only work with y-axis?
No. Does it only work with y-axis? No. It'll work with any axis, vertical or horizontal. This part 2 is going to be horizontal. We're going to flip things a little bit next day, but yeah, any axis you can rotate this around. Now, there's a little bit of a. We'll talk about that in a bit. We're going to get there, but the radius is going to change slightly. Okay, that's all. The radius, the format is going to be the same, but if there's a different axis of rotation other than y equals 0, then we're going to have to acknowledge that. So I'm just going to do this one now, and it's going to be, obviously, the radius is going to change, so it's going to be x, either plus or minus something, or it's going to be something plus or minus x. So we'll get there in the next level of examples. So a couple things you want to note, that this is a constant, frozen, sorry. This is a constant 2 pi, so we can take that out, and we're going to simplify this over here, all right? So the volume, computer, volume is going to be equal to 2 pi times the integral from 0 to 3. And remember integrals, okay? Like these limits of integration have to be x values, because this is dx, okay? And now these are all x's in here, so those all have to match up. So if you're like, oh, do I go up, 0 to up? No, you go in the same direction as the dx, same direction, okay? So this is x direction. Okay. So we've got x, and this simplifies to just 2, right? So x times 2 is 2x. So really the height is 2 units, always. So that's kind of cool. It doesn't always work out like that. You might have some graphs that vary like this, and another graph that goes like this, right? So it's not always going to be the same, but in this case, it's actually a constant, which is going to make our integral real easy. Okay, so now we can do this easily by hand. 2 pi, you can just leave out there. 2x, the integral of 2x is going to be x squared. Yeah, from 0 to 3. So the volume is 2 pi times 9 minus 0. The volume is going to be 18 pi units cubed. Okay, so cylindrical shells stacked, nested into, like those Russian dolls or whatever, where you take the cap off and there's another littler one just inside, and you take the cap off that one, there's another little one inside. So this is the same kind of thing. These cylinders are kind of nested in each other a little bit. Okay, any questions on that so far? All right. Please access this. Okay, so go to mrmathwell.com. Okay, so what you'll find on there, on your AP, Advanced Placement, Calculus AB, this is Cylindrical Shell Method right here. Now, this link right here is the online textbook, okay, for this, just for a section. This is a Stewart Calc online, and I'm going to use some of these questions and answers. Now, you'll have the solutions as well as in this link. This is from your FINI text, and last section when we did washer method, I think you did solids of revolution, these same questions using the disc washer. And so I'm going to ask you to just compare this shell method for some practice, to do the cylindrical shell method for some of the same questions, see if you get the same answers, okay? But we're going to focus on this here right now. So if you click on that, let's see, this should show up. All right, it should look just like this. It's just a section from this book, but I like this. Now, this explanation, these diagrams, you can take a look at those if you want. I've tried to simplify things. Didn't use some of the the summation notation. Kind of went straight to integrals that we know. Okay, but what I want you to focus on is the practice examples here, so the exercises. So these are going to be handy for you. I'm going to assign some of these for you, and you do have the solutions and answers there, so you can check your work. But this is the first question that is in that document. And it says this: let S be the solid obtained by rotating the region shown in the figure below. So here's the region, the area right here, about the y-axis. Explain why it's awkward to use slicing, and by slicing they mean, you know, the disc or washer method, to find the volume of S. Sketch a typical approximating cylindrical shell. What are the circumference, or what's its circumference and its height? Use the shells to find V. So the first part is a little bit weird. It's like, how is this difficult? Okay, well, this is difficult to use washers, and I'm just going to, you don't have to write this down, but this would be, you know, these washers would kind of look like there's the hollow middle part, you know, and here would be the outer part, okay? So this big fat washer here, all right? But how do you get a radius, you know? How do you subtract? How do you find the difference between, you know, a function and itself on different parts of the function? Like, well, how do you subtract it? How do you find, you know, the width of this washer? So it would be awkward because you only have one function that provides the outer and the inner function. You could say just that. There is only one function involved. It's not like you can subtract two functions to get the you know, the width of that washer. How you would actually have to do this is you would have to find out where this maximum point is, I guess, and you would have to, you know, make a vertical line. I'm not going to get you to do this, of course, but what you'd want to do is you'd want to rotate this part through space by doing the washer method like this. You see these washers here, only going from here, and you would find that part first, and then you would go from this x value to 1, and you would find these washers, okay, and you would add these ones on as well. So it would be really, really weird. You'd have to split that function into two pieces, so that's not going to be good. But if you consider the shell method, check this out, okay? Here's one of the really small cylindrical shells, okay? Here's a larger one, okay? And here's the tallest one at the point that would be sort of the apex there. That's the tallest one, and it's going to be, you know, the widest one. Oops, what did I do there? Okay, you kind of see that. So how is this? This is way easier because remember, the height is what changes, the height, and that's just the function. The height is just the function. There's only one function. The height is the function minus 0, right? The radius is simply values of x. So this becomes really easy to find the solid of revolution, okay? So what's its circumference? Okay, so the circumference is 2 pi r. That is, circumference is 2 pi. The radius is just x. And the height is just the function, x times x minus 1 all squared. That's the height wherever that function is. So that obviously the height changes as the function changes. But we'll let the integrals kind of take care of that. Use shells to find V. Okay, so let's see if we can kind of get this going. So the volume of these of this rotated through space is going to be, we're going to put 2 pi outside, remember, 2 pi is outside. The width, the kind of the thickness of the outer walls is in the x direction. So we know it's going to be dx, all right? That'll be handy later because when we use cylindrical shells this way, the width is going to be in the y direction, so we're going to have dy. So that's part 2, see? Not going to be terrible. We're just going to flip it 90 degrees. So this is dx, so that means that these have to be x. Okay, those have to be x. So where am I going to go? Well, I'm obviously going to start from here, and I'm going to end here. So from 0 to 1, you see that? So my limits of, or my limits of integration are from 0 to 1. And of course, that has to do with the radius. The radius is just going to be x. Okay, it's just going to be your x. So 2 pi r is x. And the height is x times x minus 1 all squared. That's the height. We don't have to subtract anything. It's just the height of the function. Well, we subtract 0, I suppose. Okay? How's everyone feeling about this? Is it seeming to make some sense? Yeah. You can visualize it. You kind of know, where the numbers go. 2 pi r h, really important. If you remember 2 pi r h, that is super important. Constant, don't have to worry about it. What is r? What's the radius of the cylinder? And what's the height of the cylinder? Is it a difference between two functions? Is it just one function? So on. Okay, so let's do this. 2 pi, 0 to 1. So this is going to be, well, I guess this could be x squared times x minus 1 all squared. Might be a good idea to expand this out, I guess. So we can do this, kind of one term at a time. Might be a good idea. So this is going to be x squared times x squared minus 2x plus 1, which further simplifies to x to the 4th minus 2x cubed plus x squared. And that we certainly can, make more space, we certainly can do by hand in a pretty straightforward manner. Okay, if you have a calculator, to do this, you'd want to get maybe a common denominator here. Do 10, 30, I guess. So it'll be 6 over 30 minus 15 over 30 plus 10 over 30. Two pi, is that 1 over 30 you get? So v equals 2 pi over 30. That's what I got. I'm just going to check this. All right, so you get a volume once you evaluate all this. You get volume of pi over 15 cubic units. Okay, any questions about that? That is the correct answer there. Yes?
If you wanted to do this, the washer method, you would have to, like...
So 2 is very similar. You're going to do that one on your own. And number 3, I'm going to go over with you. So there's selected answers on that document that I have linked there. They don't have all the answers, just selected answers. So you're going to be able to do some, check the answers. Others, I'll get you to do, and I'll check to see if you have the same answer as me. All right, so number 3, this doesn't give us a diagram, but instead it just gives us a listing of boundaries and some instructions. So use the cylindrical shell method to find the volume generated by rotating the region bounded by the given curves about the y-axis. Sketch the region and a typical shell. Okay, so for number 3, let's just focus on one thing at a time here. We're at number 3. Okay, so we have 1 over x. Now, if you're unsure of what the graph of 1 over x looks like, just do a table of values, right? 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, and 1 over 4. So 1 over 0.5 would be 2. So we are looking, it's looking something like this, right? It's something looking like this on the right side. And it would be good for me to try and hit some of those points. Even worse. Oh, well, whatever. Okay, so it looks something like that. And we're going to go from y equals 0. So that is this boundary here. Y equals 0. X equals 1. So here's 1. It's a boundary there. And x equals 2. So here's 2. Okay, so it's this region right here that we want to rotate through space about the y-axis. So you can kind of see that we're wanting, there's the, if we were to take a cross section, right? This is what we want, and there's going to be, you know, it'll be like this through space, right? Front, back, and everything, with the hollow middle. You see that? Just kind of rotate it around. All right. Okay, so if we think about the cylindrical shell method, I'm highlighting a cylindrical shell right now. This would be the first of the cylindrical shells right here. Awesome. And I am going to go, so volume is going to be 2 pi RH, right? Okay, now R and H, I know we have to work on an integral. This is going to be dx. So I am going from 1 to, in the x direction, to number 2. So limits are from 1 to 2. And I'm trying to find the wraparound parts that have a radius that is equivalent to x. You see? The first one has a radius of 1. Well, that happens to be just the x value. The next one would have, 1.1, let's say. Well, that's just the x value, 1.2, and so on, 1.5, 1.6, 7, 8, to 2. So the radius is just x here. It corresponds to all of the just the x values that you would see in between there. That's would actually be the radius. Now the height is going to be simply this function value. So the height is going to be 1 over x. So again, your key for cylindrical shells, the key is 2 pi RH. R is going to be your x, or x plus something, or x minus something, or something minus x, and so on. And the h is going to be just the function height, or the difference between any two functions that might be there. So volume is 2 pi. We can simplify this. X times 1 over x is, yeah.
Can you give an example of when x, like r would be like x plus 2?
Yes, coming.
Okay.
Yeah, coming. In the next set of examples. I'm going to do one more example before this class is done. Yeah, but anyways, I'll rush through this one, okay? So x times x is just going to be 1. So this is really just the integral of 1 dx. So you can imagine this becomes pretty easy. The integral of 1 is just x, evaluated from 1 to 2. So 2 pi times 2 minus 1, sorry, 0, I guess that's 1. So the volume is 2 pi units cubed. Check that. All right, so 2 pi units cubed was the answer for number 3 there. So here's the last section I'll do with you today in today's lesson. What happens if we want to rotate not about, x equals 0, but about x equals something else, right? It's a vertical. So that's going to affect the radius, right, of those cylindrical shells. So you should be able to think through this one pretty clearly. In 15, it's not too bad. 17, I'll probably try and set you up with both of these before the end of the class here. So 15, let's take a look at that one. So y equals x squared. I'll draw the just the diagram over here. So we got x squared, and we're going from x equals 1 to 2. So 1 to 2, and above the x-axis, which is y equals 0. So here is our region. And we're trying to rotate this about what? About x equals 1. So our axis of rotation is now here. Okay. So if we were to draw the cylindrical shells, here's one representative cylindrical shell. And the radius here, you see, the radius is not corresponding to x, because this value right here would be 1 point something, and the radius is certainly not 1 point something. But it would be 1 point something minus 1. And this one, radius here at the very end, would be 2 minus 1. Okay? So it's always kind of minus 1 here. The radius is this value, 1.8 minus 1. 1.5 minus 1. So what you do is you keep in mind 2 pi RH. We'll focus on R here. The volume is going to be 2 pi. The integral from 1 to 2, and the radius here now is going to be, okay, let me erase some of this. It's going to be your x values, but the radius starts at, this is 0 radius here at 1. Okay? So it's going to be x minus the axis of rotation. Okay? If it's to the left of your region. So it's going to be x minus 1. Okay, so a little, by way of explanation, I'm going to zoom in here now. So if we were rotating about the y-axis, just for comparison, then the radius of the cylindrical shell, the first one would be a radius of 1. You see that? But that's not the case. We're rotating about this line, so the radius at 1 is actually 0. So it's not 1, it's actually 0. And here it's not 1.5, it's actually just 0.5. And here it's not 2, it's just 1. So what do all those have in common? We have to subtract 1 from whatever x value is. So it's x minus 1. So do your x minus your rotation of axis if it's to the left of your area. 17 is going to be when the rotation of axis is way over here at 4, which we'll do that one next, okay? So let's finish up this one. Well, actually, you know what? I'm not really going to finish up this one. I'm just going to set it up and you can actually do the work. So that's r. H, of course, is just x squared, right? Because you have 0 here, you have x squared on top. So it's x squared minus 0. That's what the height is for these cylindrical shells. And then dx, okay? So you can go ahead and finish that one on your own, number 15. And then number 17, I'll just go over quickly in the last 7 minutes or so that we have. All right, so let's take a look at 17. If you haven't done 15 yet, just you can just put a hold on that, leave yourself some space here. Number 17 is a similar situation. It's y equals x squared again, above y equals 0, between 1 and 2. But the rotation of axis is all the way over here at x equals 4. So before, we were rotating this way, right? Around the y and then around the 1. Now we're rotating about the 4. So we are actually flipping through space the exact opposite way, you see? We were rotating this sort of this way around an axis. Now we're rotating, not that way, but we're rotating this way. So the nature of the shape of that solid is going to change quite drastically. Okay. So how does that work? Well, again, the key here is 2 pi RH, and the key is R, trying to find R. And that might be, that's the toughest thing when we're talking about the axis of symmetry. So the radius of this, okay, now let's think about this. The radius, how does it relate to x? Well, the first little shell here, the shell that has the smallest radius is actually 4 minus 2, right? A larger radius is going to be 4 minus 1.5. The larger radius then, at the end, the largest radius is going to be 4 minus 1. So the radii are actually getting larger. So as x grows, it's not a good idea to x plus 4 or x minus 4. Instead, whatever's the furthest to the right, if it's the region furthest to the right, then it's x plus or minus something. If it's the axis of symmetry furthest to the right, you got to start with the axis of symmetry. And in this case, the radius of these cylindrical shells that I've drawn is going to be 4 minus the x value. It's going to be 4 minus the x value. So the first one's going to be 4 minus 2, you see, is 2, radius of 2. Then we're going to have 4 minus 1.5, which is going to be a larger radius of 2.5. And then 4 minus 1 is going to be 3. That is the largest radius that's represented. Okay? So the radius is 4 minus x here for this one. So the volume is 2 pi times the integral. Now, I'll come back to this. It's going to be dx still, obviously. But the radius is going to be 4 minus x, and the height is going to be still the height of the function minus 0. So that's going to be your x squared. Now, the final piece here is we need some x values to go on the limits of integration. So what do you think? Are we going to go from 1 to 2 again? Are we going to go to 4 somehow, or what? Remember, these are x values, and we're using x in our radius. So we want 4 minus 1 to be the largest radius, and then 4 minus 2 to be the smallest one. So those cylindrical shells, as far as the x direction, are going to go from x equals 1 to x equals 2. So the x is going to change from 1 to 2, so that the radius changes from 4 minus 1 to 4 minus 2. Okay? Tricky. That's tricky. So we're still going to go from 1 to 2 here. So there's the diagram. This little region that we drew over here swings out this way. And so the radius is going to be, 2 units here all the way to 3 units wide here. So the radius is going to be 4 minus whatever the x value is, ranging from 1 to 2.
This is a reminder that musical practice.
So on that online document, please do number 1 to 7 and 15 to 18. So 1 to 7 and 15 to 18. And tomorrow we will talk about part 2, cylindrical shell method, rotating about the y-axis or a horizontal axis of reflection there, rotation. Okay, so 1 to 7, 15, 18. Any questions?